Hello, this is Mr. Weideman, and this is Lafayette High School Functions in Trigonometry. And today we're going to start our first lesson in section 6.2. Sum and difference formulas. And the key to this stuff is look in on these pages 565 and 660, or look in the back flap of your textbook. And I can see there's 6 different formulas, 2 for sine, 2 for cosine, and 2 for tangent. Don't worry about memorizing these formulas for right now. Okay, for this particular section and this particular lesson, make sure that you have all 6 of those formulas right in front of you. Otherwise, this is going to be really difficult. Well, we're going to be using these formulas, and so it's important that they're right there in front of your eyes, and so you can kind of see the format. And what are these formulas going to be used for? Well, the first thing we're going to use them for is calculating exact values of angles that are not on the unit circle. And the way we're going to accomplish that is we're going to use combinations of angles that are on the unit circle. And we're going to add and subtract them and get some that are not. And we're going to see how that pans out here in a little bit. And then we're going to do, these are also, we call them formulas, but they're also called, identities. And just like we have our Pythagorean identities and reciprocal identities, and we use those to verify and do proofs and algebraic substitutions and all that kind of good stuff. Well, these are just some more relationships, more identities that we can use to simplify expressions. And we'll be getting into that a little bit later on. Okay, so the best way to get into this is let's just do an example of what we're going to do in part A. I'm going to use the difference formula to calculate the exact value of an angle that is not on the unit circle. Okay, so let's start off with this expression right here, cosine 15 degrees. And this is an example problem you should probably have in your notes. Okay, obviously 15 degrees is not on the unit circle, and yeah, I know we can just punch it into our calculator, but it says the exact value. Okay, so that means that the only exact values that we know are the guys on our unit circle. And that is not on our unit circle, but 60 degrees and 45 are on the unit circle. So if I take 60 degrees minus 45 degrees, then I come up with that 15 degrees. Okay, so that's one of my subtraction formulas, and this is what it looks like. Those little funny-looking symbols in your book. That is a Greek letter alpha and a Greek letter beta. So I'm just going to use A and B, and A is just one of your angles, and B is your other angle. And in this case, I'm going to go angle A minus angle B. And it says if I'm going to do that, well, this formula, albeit kind of complicated, will yield the exact same thing. All right, so what I'm going to do is I'm going to say that my 15 degrees is done by a subtraction of 60 minus 45. So the 60 degrees becomes my angle A, or alpha, and my 45 degrees becomes my B, or beta. And I'm literally going to substitute in. Everywhere I see an A, I'm going to substitute in 60 degrees. Everywhere I see a B, I'm going to substitute in 45 degrees. All right, what we see now is we have an expression. It's saying, cosine of 60 degrees, cosine of 45 degrees. Well, those are angles that are unit circle, so we can actually go to our unit circle and get those values. So that's what we're going to do here. We're going to go to our unit circle, and cosine of 60 degrees is 1/2. Cosine of 45 degrees is root 2 over 2, so on and so forth. Okay, and now we're just going to perform the multiplication and the addition. So we're just going to multiply these two terms together. And 1/2 times root 2 over 2, that's root 2 over 4. And then the other term is root 6 over 4. And this is fine. You can leave that just as this expression right here. That is your answer. You can get a little bit fancier and write it like this because it has a common denominator. Okay, but if you were to actually punch this into your calculator, and you'll get a decimal approximation of root 2 plus root 6 over 4. And that's how we use these formulas. Okay, so let's do another problem. This time, instead of dealing with degrees, we're going to use radians. Now, my advice for this is, since these guys are not going to be on your unit circle, like for instance 7 pi over 12, what the heck, and you just go, wow, what do I add and subtract to get that? I need a common denominator of 12 and blah 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 blah. It gets pretty icky. My advice to you is let's convert that 7 pi over 12, let's convert it to degrees. Simply because if you convert 7 pi over 12 to degrees, it's a little bit easier to see what combinations of angles on the unit circle will add up to. In this case, it turns out to be 105. Okay, so it turns out 7 pi over 12 is 105, and that is going to be a combination of 60 degrees added to 45. Any combination will work. You just have to make sure that the angles you're adding together or subtracting are on the unit circle, which means that it's going to be some sort of multiple of 30 degrees, and it's going to be some sort of multiple of 45 degrees. So you don't have to weed through like an infinite possibility. All right, these combinations, whether the addition or subtraction, have to be some combinations of angles that are on the unit circle. All right, in this case, we picked 60 degrees and 45, which turns out to be pi over 3 and pi over 45. I mean, if you wanted to, at this point, instead of working in pi over 3 or pi over 4 for your angle A and angle B, you could work in 60 degrees and 45 degrees, and that's fine. It's going to come out just fine. Because, again, we're going to go to our unit circle, and I'm going to look up the sine of pi over 3. I'm going to look up the cosine of pi over 4, blah, 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 blah. Okay, and it doesn't matter if you go to your unit circle and look up pi over 3 or 60 degrees. You're going to get root 3 over 2. All right, so we're going to multiply these together, and now we're just really doing algebra. And then I'll combine those because they have the same denominator, and that's our final answer. So I kind of strongly suggest that turn your radians into degrees, and the numbers are going to be a lot easier to work with. You're going to have these whole numbers instead of pi over 3s, pi over 2s, pi over 4s, and all that other kind of stuff. Okay, you guys try one. Let's go to page 654, checkpoint number 4, and pause the video and see if you can find the exact value of, what are they asking for, 5 pi over 12. And I'm going to kind of give you a hint. That's 70 degrees. And it really doesn't matter if you use the sum formula or the difference formula, you're going to get the same answer. All right, let's see how you did. Did you come up with this answer? Root 6 plus root 2 over 4. If you did it correct. If you're confused, let's take a look and see how we made this happen. Okay, so the combination I used was an addition of 30 degrees, pi over 6, and 45 degrees, pi over 4. Those add up to 75, which is the same thing as 5 pi over 12. Again, what I did is I converted it to degrees just so the math was easier. You know, what's going to add up to 75? And I go, oh, okay, well 30 and 45. All right, and then it's just a matter of plugging and chugging, and there's the math. Okay, what I'm going to do now is to go on to our next part. We're going to kind of be using these formulas backwards, if you will. And it's a little bit like doing a proof, or it's how we're going to do the proof. And this video is getting a little bit long, so I'm going to stop it right here, and then I'm gonna carry this on into the next video, and we're going to find out how I'm going to do the cosine of 80 degrees by using these formulas backwards.